Welcome to the community of
engineers, the change agents in the society. In this video, we will discuss analysis and design of beams for bending. Let's say we have a beam. Let's say this is beam AB and this is subjected to transverse loading P1 and P2. Now, what is a transverse loading? Let's say if this is the x-axis, this is y-axis, and this is z-axis. Now, in this case, along the major dimension of the structure, this is the longitudinal axis, and along the minor directions, along y and z, these are the transverse axes. Now, for the case of beams or structural members which are subjected to along the minor directions mean the transverse loading. Specifically, the loading along y-axis would be considered in this analysis. Now, the sequence of analysis and design of beam for the bending would be: first we discuss the types of supports, then types of beams, then we will discuss types of loads, then calculation of shear forces in beams, then calculation of bending moment beams, and more based on the information of this we construct a shear force diagram and bending moment diagram. Now, first of all, we talk about types of supports. Now, in this, the first one, that is the hinged support. Also known as the pin or riveted support. Let's say we have a beam and this is supported by a pin. This is a sign of to show that this is a pin support. Now, in this case, Let's say we depict pin or hinge like this. Here we use a pin, and this is supporting a beam. Now we have to calculate or see the number of restrictions posed by this application of this port, because on the basis of number of restrictions we are going to calculate the number of reactions. Now if we consider this is the x-axis, this is the y-axis, and out of the board that is the z-axis. Now considering this hinged up pin port, we see that because of the application of this pin port, there is no possibility of translation along x-axis. So when this is the translation along x-axis is restricted, there is no possibility of translation along y-axis. Again, the moment along y-axis is restricted. However, there is a possibility to rotate this beam about z-axis. So there is a possibility, so there is not going to be any restrictions as far as the rotation about z-axis is concerned. At the same time, we are not going to consider the translation along z-axis. So if you have a pinned or riveted beam, so number of reactions you have to calculate, these would be 2 in place of this port to show the free body diagram. Now what is the free body diagram? I have just used a word free body diagram. Once all the supports are removed from the figure, and replaced with the reaction forces, or commonly we say that reactions. So this is, or this figure is known as the free body diagram. Now we have just considered one of the sport, that is hinge sport or the pin sport. Now we talk about the roller sport. Sorry. And the sign of roller sport is this, that a hinge, and under that you place rollers. So this is a roller sport. Now in this case we can say the sport which provides loading in one direction only. So here we see, again considering the x, y and z directions, there is a possibility of motion or movement along x-axis, means no restrictions. However, there is a there is no possibility of movement along y-axis, so there is a restriction. And there is a possibility of rotation about z direction. So in this case the number of restrictions would be 1. Consequently the number of reactions would be 1. Now considering a fixed board, also known as the built-in sport, we have a beam, and this is supported with a fixed board. Fixed board. Now for the case of fixed board, the number of reactions would be 3, and consequently the number of restrictions 3, the number of reactions would also be 3. Now the types of beams. The first type, that is the simply supported beam. A beam which is supported at the extreme ends. Let's say we have a beam and this is supported at one end with the pin support, and on the other extreme end with the roller support, and subjected to a load P. Now if we just draw the free body diagram, for this case, so showing the number of reactions to replace the supports. So this is the load P, and here the number of reactions are going to be, or let's say this is A and this is B, and the length that is of L. Now at A the reaction is going to be RAY, and here we would be having RAX, and at B we are having only one reaction, that is RPY. So this is the free body diagram for the case of simply supported beam. Now we have the cantilever beam. One end in this cantilever beam, one end of the beam is fixed by the fixed support, and the other end is free. So like this, let's say this end is supported with the fixed support, and let's say this is A and this is B. Now this is free end. Now this is the free cantilever beam. Then we have the overhang beam or overhanging beam. A beam with some unspotted length or overhang position. Let's say we have a beam and this is spotted with a pin spot at, let's say, A, and at point B with the roller spot, and this C end is unspotted. You can say unspotted length. Then we have the continuous beam, a beam with more than two spots. Spots is known as the continuous beam. Let's say we have a beam. Now this end is spotted with pin spot, and here we have the roller spot. Again at this point we have the roller spot. So at point A we have pin spot, at point B we have roller spot, and again at point C we have the roller spot. So this is the representation of continuous beam. Now the types of loads, and in fact these are the mechanical forces. So we may have two types of loads, that is the concentrated loads or the point loads or the distributed loads. Let's say we have a beam AB and this is subjected to, let's say, load P1, load P2, and also we have a load of some length. This is denoted with omega. Now in this P1 and P2 are the concentrated loads and omega is the distributed load. Further, we have two types of concentrated load, the centric load. In this case, let's say if we have simply supported beam, pin support at one end and roller support on the other side, and this is subjected to a load that is situated right at the mid of the beam, and if the total length of this beam AB is L, now this length is going to be L by 2, again this is L by 2. So this is the example of centric load, or we may have the eccentric load. Again, let's say we have the beam AB supported with pin and roller support, and the application of load in the form of concentrated load. Now this is not situated in the middle of the beam. Now let's say this is total length. Now let's say this is length A from the A to the application of load. So this length is going to be E minus L minus E. So this is the example of eccentric load. Further, we have two types of distributed load. The one that is uniformly distributed load, UDL. In this case, the load is on beam AB is all along the beam, and this is denoted with sign omega. The same load that is starting from point A till point B is subjected to this uniformly loaded and denoted with this omega. Now we are here in this case, the magnitude of the distributed load magnitude of the distributed load denoted with this capital W. We can calculate with this W is equal to omega, and let's say this is the length L into L. Now this omega, units of omega is Newton per meter. So The unit of magnitude of the distributed load would be newtons, because omega is Newton per meter, and this is multiplied with the units of L, that is in meters. So this is going to be in newtons. Now further important thing is the point of application, or the line of action of this distributed load. So the load will pass through for this uniformly distributed load. The load will pass through centroid of the load of the load distribution diagram. Means this magnitude of load would be in the centroid of the distributed diagram. Now if we talk of the other, that is uniformly uniformly varying load, UVL. The previous was the UDL, the uniformly distributed load. Now uniformly varying load. Now in this case the load is linearly varying. Let's say we have a beam AB, and here we have a load that is linearly varying. So this is the example of uniformly varying load. So again this is denoted with the sign omega. Now here at this point A we have the omega value, that is 0, and here we have the, at B point we have omega maximum. Let's say this is denoted with omega naught. Now to calculate the magnitude of uniformly varying load, again denoted with sign W, capital W. Now this would be a typical case for the triangle. The area for triangle, that is half BH. Now in this case, this is the area under this is going to be, let's say, the length, total length, that is of L. So the magnitude of UVL is going to be of, now B is the length into this H, the total height, that is omega naught. So the value of W is going to be of omega naught L. Now the application of this, that is the point of application of the line of action, would be here from the zero end, that is going to be 2L upon 3, and from the maximum omega naught value, this is going to be L upon 3. Now this is for the case of uniformly varying load. Now we will talk shear force, calculation of shear force and bending moment in a beam. Now let's suppose we have a beam AB, a simply supported beam means one end that is supported by the pin support and the other end that is supported by roller support is subjected to a uniformly distributed load omega. The length of the beam, let's put L. Now as a first step, you make a free body diagram of this beam by just removing the supports and replacing with the reactions. So here we have the RAY and here we have RAX, here we have RBY, and this is subjected to a uniformly distributed load omega. Now after that, we go for the calculation of shear force and bending moment in the beam. Now as a thumb rule, the shear force and bending moment is never calculated for the entire beam. Rather, shear force and bending moment is always calculated at a section of beam. Now, to calculate the shear force in beam, considering same beam, this is RAY, RAX, RA, RBY, and this is subjected to uniformly distributed load omega. The length of the beam, that is L. Let's say this is, here we have, if this is X, so X 0, here we have the X value, that is L. So for the case of calculation of shear force in the beam, summation of all the vertical forces means the transverse forces acting up to a section, up to a section. Let's say we cut a section up to X. So summation of forces along y-axis is 0. So up to this, here we have the force, that is RA plus omega into X. So this is omega up till X. Now for the case of calculation of bending moment in the beam, so this is going to be summation of moment of all the vertical forces vertical forces up to a section. Summation of a moment at X is equal to 0. So here RA y, since it is at 0, so 0 plus omega x multiply the line of action, the application of the force is going to be W at x by 2. So this is going to be half omega x square is equal to 0. Now we will discuss relationship between shear force and bending moment. Let's say we have a simply supported beam. One end is supported with the pin support and the other end with the roller support. Now the length of the beam, let's suppose, is L, and from this side this is x is equal to 0, this is x is equal to L, and this is subjected to a uniformly supported load omega. And just to draw a free body diagram, let's say in this free body diagram, this is the reaction, this is R1, and reaction at B, that is R2, and this is subjected to the UDL of intensity omega. Let's suppose we cut a section at length x, and this length is of dx. Now we just draw this section, a large view of this dx section. This is 1, this is 2, and this is subjected to the same very load omega. Here we have the shear force, that is V, and this is the bending moment, and here we have V plus dV, and the bending moment, that is M plus dm. Note that notations we use for the shear force, that is V, and the bending moment, that is M, and intensity of load, of load with the omega. So as we just described that the shear force we calculate, that is the summation of all vertical forces, that is sigma Fv is equal to the vertical forces or the shear forces, Fv is equal to 0. So considering this, we can write this V, since it is upward, so we have the positive sign minus the magnitude, that is going to be omega into dx of total distance. So minus V plus dV is equal to 0. After removing this bracket, we get that V minus omega dx minus V plus, sorry, minus dV. So after cancelling this V, we are left with minus omega dV upon dx is equal to minus omega. So this we can write as the rate of change of the rate of change of shear force, rate of change of shear force with respect to x, the x is the location of the section, is equal to the intensity of load, that is depicted with this expression dV upon dx is equal to minus omega. Now we go for the relationship between shear force and bending moment. So considering same section 1 2, that is here we have the shear force V and bending moment M, and here we have the shear force V plus dV and bending moment M plus dm. Now the length, that is of dx. Now here the magnitude of this section at C, let's say at point C, W is going to be omega into dx, that is the magnitude of this uniformly distributed load that is acting at distance dx upon 2. So for the case of bending moment, that is summation of moment of moment of all vertical forces, that is at point C, let's say summation of point C is equal to 0. So starting from left we have moment m plus we have v multiply with dx upon 2. We are taking moment about this, so v into dx upon 2 plus omega into dx, that is the magnitude that is same at 0, plus we have v plus dv again at distance dx upon 2. On this side again we have the same distance minus m plus dm is equal to 0. After opening the brackets we have v dx upon 2, so this is 0, so v dx upon 2 with this multiplication, and then we have plus dv dx upon 2 minus m minus dm is equal to 0. Now after cancelling these terms m with minus m and considering this term as product of very small terms divided by 2 is going to be very small, so neglected. So we are left with v dx minus dm is equal to 0, or we may write this as dm upon dx is equal to v. So this is the rate of change of bending moment with respect to x will be equal to the shear force. So in fact we have dv upon dx is equal to minus omega, the intensity of the load, and dm upon dx is equal to v. Now with this we end our discussion here.